Okay, so we're moving on to the next section of the course today. We're building on some of the ideas from evolutionary game theory, which we spent the last couple of weeks looking at. But we're going to be extending some of those ideas, which kind of mirrors how this particular area of phenotypic evolution modeling developed during the course of the 20th century. So why are we doing that? Well, the evolutionary games that we've met so far, they've all tended to be pretty simple. And simple is not necessarily bad, but I'd probably actually say that they've been simplistic, and overly simplistic. They do give you some important insights. We've had some important insights about things like sex ratio. Again, it was probably an oversimplified model, but it tells us something, if you remember last lecture, about how maybe the reason in many populations you see equal sex ratios at birth is more to do about payoffs and fitness and nothing to do with Mendelian segregation. And it also matters that there's also this sort of balancing effect where producing more sons, say when there's lots of females around, isn't necessarily advantageous. It all comes down to, in that case, all about investment into offspring from parents. That's the key thing that this determines the sex ratio. We also saw some insights about things like matching dynamics, that there might not be some optimal trait. We know when we did the matching penny scenario, maybe tells us something about the nature of host pathogen or host pathogen or prey predator interactions. So there's lots of cases like that. We also saw examples from cooperation as well, which is a big thing in evolutionary biology, trying to understand altruism. Why might there be cooperation in animal societies? And we end up seeing, even in sort of very simple organisms like Dictyostelium, remember those slime molds that produce these fruiting bodies, there is evidence of cooperation. So understanding these games does give us some useful insights, but they're also a little bit flawed in how they approach evolution. One of these is that the games that we've been considering are all discrete games. Now, in of itself, that's not necessarily a bad thing. So we've been assuming that we've had finite games. We'd expect there to be a finite number of strategies. Perhaps that's not too unrealistic. A finite number of pure strategies, that is. Obviously, you can have an infinite number of mixed strategies. In reality, we probably expect there to be much more variation. Typically, we've just been dealing with 2 strategies in a population, which is a very simplistic way of looking at it. This is somewhat like having a population genetics model where there's just one locus and there's 2 alleles. I mean, we did those models to start the course, but you're quite limited in terms of what you can do. If you remember, we started looking at multi-locus models because they're more representative of real populations. In a similar way, we need to start thinking about a wider phenotypical strategy space. So that's one limitation in terms of the game theory we've looked at so far. But really, the big one is this second one here. So evolutionary game theory essentially just focuses on steady states. It focuses on the endpoint or potential endpoints of evolution. We looked at these in the form of Nash equilibria. If you remember, a Nash equilibrium is telling you essentially there's no incentive to deviate from your current strategy. So it tells you something maybe about stability. And we also have this stronger definition of evolutionarily stable strategies. Okay, the fact that no other strategy would be able to invade. So there's some sense there about thinking about those steady states that are encapsulated in Nash equilibria and evolutionary stable strategies, and we'll meet these evolutionarily stable strategies in a slightly different form during this section of the course. We'll be leaving Nash equilibria behind. But one of the key things is that evolution doesn't have this foresight. There might be an optimal strategy for the population. And often we saw that there were maybe 2 evolutionarily stable strategies, right? But which one are you going to go towards? There's nothing about the dynamics in these evolutionary game theory models. And that's one of the big flaws. Okay, so you just sort of jumping and say this is the optimal thing for either an individual or for the population. We know that what is necessarily good for an individual is not necessarily good for the population. Jumping straight to those steady states is a bit problematic. Okay, it presupposes that evolution is going to take you there. We want to think now about more of an adaptive process. So you think about this dynamic evolutionary process where there's a gradual invasion and replacement of strategies, phenotypes that are slightly different from each other. This is not the only way of modeling evolutionary dynamics. We could model big jumps in traits. We're going to model a relatively smooth changes in strategy space. So we'll move towards this direction. And this all comes under the umbrella of something known as adaptive dynamics or evolutionary invasion analysis. Okay, so by the end of today, you should understand some ideas about what adaptive dynamics is and a bit about evolutionary invasion analysis. Like I said, we'll be building this on more in the coming weeks. We're going to talk today about replicator dynamics, which is a way of starting to transition from evolutionary game theory to think about more about this dynamic process of evolution. We'll talk about ideas of resident and mutant phenotypes. So you can think of this as competition between two strategies, but in a slightly like a particular way of setting up this model. We'll talk about ideas of separation of timescales and something called weak selection as well. Okay. So evolutionary game theory helps us to determine optimal strategies usually, and it generally focuses on payoffs for a particular interaction between pairs of individuals. And we want to try to generalize this to get some dynamics out of it by thinking about interactions between not pairs of individuals, but different strategies. Okay, so that's very similar to the sort of the strategy space that we have in evolutionary game theory. But this more general model of phenotypic evolution. So you remember a phenotype is just the characters or traits that individual organisms have, whereas their genotypes, the genetic underpinnings of those traits. And the phenotypes could also be determined by environmental factors as well. So your height or your eye color is a phenotype. So the one thing we're going to do is we're going to assume, rather than having this discrete strategy space, that we're going to have continuously varying traits. Okay, so for example, body size or some sort of preference in terms of where you prefer to nest or what kinds of food you prefer to eat. We'll think of these as something that might be continuously varying. So the food one, for example, could be birds with a particular size beak are better and prefer eating seeds of a particular size. If the seeds are too small, they can't get hold of them. If they're too large, then they can't eat them. That kind of thing. And I mentioned the idea of like a nest site again. You might prefer nesting in a particular area. Okay, so we're going to think about those continuously varying traits as we build up towards these evolutionary dynamics. And like I said, we can achieve this through evolutionary invasion analysis. But what we're first going to do is look at something called replicated dynamics as an intermediate step between these two areas. Okay, so what are replicated dynamics? Suppose we've got S strategies. So S is just some number, S different strategies, or more generally, I'm going to be moving towards talking about these as phenotypes typically rather than strategies. Strategies sometimes makes you think that it's just about behavioral aspects. Really, we can think about, because there is a genetic underpinning to these things, we're talking about phenotypes. So things like body size. You can think of that as a strategy that evolution is choosing, natural selection is choosing. Okay, so we think about phenotypes in population. We've got S different phenotypes. One way of thinking about these is that we have a unique allele at a single genetic locus. Okay, so if we've got AI as our allele, so A1 is just strategy 1 or phenotype 1, A2, phenotype 2, and so on. And then just like before, we're going to construct a model like we did in our population genetics section of the course, where we can model the dynamics of essentially these different alleles. Okay, so if we let n sub I be the number of individuals with phenotype I, and capital N be the total size of the population, so just the sum over all of the different phenotypes, we've got S different phenotypes. That's going to be our total population size. Then pretty straightforward, the frequency of phenotype I, PI, is just going to be NI over N. Okay, very straightforward. We're going to define this to have a per capita rate of change. So per capita rate of change of the number of individuals with phenotype I is going to be ultimately given by MI, which is going to be 1 over NI dNI dt. This is actually slightly incorrect, I realize. This shouldn't be which has per capita rate of change. This should be NI as per capita rate of change. We want to ultimately work out what are the frequency dynamics. Ni has per capita rate of change. Mi is equal to 1 over Ni, dNi dt. We haven't said what dNi dt is. This M, by the way, is very closely related to our W for fitness. This is actually, M is named after Thomas Malthus, who did a lot about population growth. You might hear sometimes Malthusian dynamics, named after Malthus. Okay, so this is all pretty straightforward, I think. We want to work out what are the frequency dynamics. First, let's work out what the per capita rate of change is for the whole population. Well, the per capita rate of change for the whole population is just going to be 1 over n, capital N, dn dt. This is saying, essentially, on average, what is each individual in this population contributing to the next? I'm going to tentatively say generation, but the next, this is the instantaneous rate of change of the population. So what's this going to be? Well, this is just 1 over n. What is dn dt? Well, it's just going to be the sum of all of our individual phenotypes, their rates of change. We've got S different phenotypes. dni dt is the rate of change for phenotype I. So the sum from I is 1 to S is going to be, of dni dt, is going to be the rate of change for all of the populations, and we want the per capita rate of change, so we divide by n. Okay, we know what dni dt is because we've defined it up here. Okay, so dni dt, just make sure it's clear, dni dt is just going to be mi ni. So we can sub that in. We'll have 1 over n times by the sum from 1 to s of mi ni. And then if you note this ni over n, we just bring the n inside the sum. This is just going to give us sum as I is 1 to s of mi times pi. Pi is the frequency of phenotype I. Anyone tell me what this is? This is a sum. And if you think of this as being the sum of the per capita growth rate of individuals of phenotype I times by their frequency in the population. So as a whole, what is this thing telling us?
Would it be something always expected?
Yeah, so we kind of given you the answer here in some ways. I should put it like this. And if we define m bar to be the mean per capita rate of change of the entire population, this is just a weighted sum, right, over all of the different types in the population, their different per capita growth rates. So weighting it by their frequency in the population, when we weight it by the frequency in the population, this then gives us an average over the whole population. So this is just a weighted sum. And this is just like before, remember when we had like a weighted version over Wi, where Wi was the fitness of allele I. If we have many alleles in a population, then when we weight the fitnesses according to their frequency, that ultimately gives us the average fitness of the population. This is analogous to our fitness that we've had before, or our average fitness. Okay. So let's restrict ourselves to a very short time interval. We'll call this dt. The reason we want to do that is we want to assume that this mi, this is the per capita growth rate of phenotype I, is going to be approximately constant. Okay, in general, this isn't going to be constant. We would expect that the growth rate of a particular phenotype might depend on interactions with other individuals in the population. There might be environmental reasons as to why this changes over time as well. But we're going to assume if we have a very small time interval, then it's approximately constant, okay, which simplifies the dynamics. So in that very small window from t to t plus dt, then, again, a little error. This should be the abundance problem of the frequency. The abundance of phenotype I grows or decays exponentially in that short window, okay? Because this mi is constant. So we can write ni t plus dt is going to be ni times t, how many individuals we had at the start of this very short window. It's going to decay or grow exponentially, and it will decay or grow according to this rate, mi dt. What you can see as dt tends towards 0, or as mi tends towards 0, then there's going to be no change in the growth rate here. Or there's going to be no change in the population size. You can see because we've got this dt, eventually we're going to move towards derivatives, so we can do about instantaneous rates of change. This exponential here comes from the fact that we've got derivatives here. Okay, so this, if you've got Malthusian growth, dni dt is equal to mi times by ni. You can solve this through separation of variables. You'll get an exponential. This is where this exponential comes from. Okay. Okay, so that's for each phenotype. Similarly, we can do the same for the total population size. The total population size, capital N, at the end of this window, t plus dt, is going to equal the total population size at the start, n of t, times by what? Any ideas? So if the abundance of phenotype I grows or decays exponentially for every phenotype, what's going to happen to the total population size? You look like you want to say, go on, have a go. Anyone?
It's
Going to be an exponent. So here this mi was telling us the per capita growth rate for that particular phenotype. We have a per capita growth rate, the whole population, m bar. So this is just going to be e m bar dt. You see, if there was just one phenotype as well in the population, then these two things are going to be equal, right? Mi would just be m bar, and ni would be m. Likewise, if there were many different phenotypes in the population, but there was no variation between them, then this mi and m bar would also be the same. But the ni's and n would be different. Okay, so there's the abundance dynamics, population sizes. If we want to work out the frequency of phenotype I going from, again, this time window pi to pi plus dpi, then pi at time t plus dt is just this pi at time t plus dpi. So dpi is just the amount that the frequency is changing in this window. Well, we just need to look at what is the frequency at the end of this window. So that's ni of t plus dt, and we've got that written above. It's just ni of t e to the mi dt divided by the total population size, n of t e to the m bar dt. You see if the population size here is constant, then this simplifies greatly, but we don't know that in general. It might not be constant in general. So this, we've got an ni of t over n of t, so that's just going to be p of t. And the exponentials here, you can think of this one on the bottom as being e to the minus m bar dt. If we multiply it, if we take it onto the numerator. So we're going to have e to the mi minus m bar times by dt. Okay. Okay, so we've got an equation now for our frequency dynamics. So we can divide both sides here by P of T. Sorry, this should be Pi T. Divide both sides by Pi of T. Note that there's also a Pi of T on this side. We'll end up with 1 plus dpi dt. Oh, sorry, not dt. dpi divided by Pi of T is going to equal e to the mi minus m bar dt. We can just take logarithm of both sides. We get the natural log of 1 plus dpi, pi of t is going to equal mi minus m bar, that's by dt. You might be wondering where we're going with this. Will be revealed in a second. So one of the things to remember is that for when we have a very small time window, in general for some very small value of x, and this is going to be a very small time window because you can think this change in the frequency is going to be very, very small because we've got a very small time window relative to whatever that frequency actually is. Okay, so as long as we take a sufficiently small time window, we can think of this as being x, and x is very, very small. And for very, very small x, we have that the natural log of 1 plus x is roughly equal to x. Okay, that's nice because that means we can drop this logarithmic term. Okay, so that means that we can write dpi dt, sorry, dpi times by pi of t, I'm getting ahead of myself, is going to be approximately equal to, so all I've done here is I'm taking this term here, this is my x, log of 1 plus x is approximately equal to x, and x is very, very small. This is going to be approximately equal to the right-hand side, which is mi minus m bar dt. Do a little bit of a trick here. We're going to assume that we think about what happens as dt tends towards 0. We're going to treat this dpi and dt as differentials. We end up with dpi dt. We multiply both sides by pi of t and divide by the dt. We end up with pi, that's by mi minus m bar. So now we've got an equation, a differential equation here, in terms of our frequency of phenotype I. It's per capita growth rate and the per capita growth rate of the population. And this should look somewhat familiar because this is quite similar to before when we had the frequency in our population genetics frameworks. The rate of change for a frequency here is equal to, for our population genetics model, was proportional to the difference between the fitness of that genotype or that allele, depending on how you set up the model, minus the average fitness of the population. Essentially, this is analogous thing. In this equation here, this last one is known as replicator dynamics or replicator equations. And this is a way of taking those strategies or phenotypes that we have in that evolutionary game theory setting and then modeling those transient dynamics. So what happens to the frequency of these different strategies or phenotypes depending on their per capita growth rates? We haven't related those per capita growth rates to their payoffs, but one could write payoffs in terms of per capita growth rates. Okay, so how would you describe then, if I was to describe the frequency or how the frequency of phenotype I changes according to replicator dynamics? Well, this is what I just described. We're seeing that the rate of change then of the frequency of phenotype I is, or the per capita rate of change, if we were to divide by pi, the per capita rate of change for phenotype I, frequency of phenotype I, is just going to be equal to the difference between its per capita growth rate and the average per capita growth rate of the population. So this is one thing that I'd expect you to be able to do if you have had an equation like this, is to be able to describe in words what it means. So I'll say that again for clarity. Here we're saying that the per capita rate of change for phenotype I is equal to the difference between the per capita growth rate of that phenotype, MI, and the difference between that and the average growth rate of the population, per capita growth rate, M bar. Okay.
Wondering if MI is like greater than M bar, will there be like a positive sort of growth in the frequency?
Exactly. And this is just like when we had the population genetics set up with the difference between WI, say, and W bar. This is intuitive, right? Things that have a higher per capita growth rate than the rest of the population should increase in frequency. So even if the whole population is growing, imagine a population is growing exponentially, but there are some phenotypes within that population that are fitter than others. They have a higher per capita growth rate. Although the population is growing exponentially, as a proportion, they'll be increasing in frequency. And this is the kind of thing you can see in, say, you can see in many populations that would be changing over time. Let's say an infectious disease, if there's, it might be growing, there might be an epidemic that's growing. So all, say, strains of a pathogen might be increasing in frequency, but some might be increasing in, all strains of a pathogen might be increasing in total number of infections. That would be our N increasing, and each of the NIs might be increasing. But as a proportion of total infections, the pathogens that are fitter than others, that are, say, more transmissible, maybe they can infect more people, those ones will be increasing in frequency. So make sure you've got those dynamics kind of squared up in your mind, that although everything could be increasing in frequency, everything could be increasing in population size, but some things could be going up and down in frequency. Likewise, the whole population could be declining, but some things could be increasing in frequency as they decline. The whole population size declines. Okay, so make sure this distinction between population size or abundance and frequency dynamics is clear. Just because, say, the abundance of a particular phenotype or genotype is going up, that doesn't mean that the frequency is going up, or vice versa. Okay. One thing to note about these replicator dynamics is that they only tell us about changes in frequency for a set of phenotypes. Okay, so this equation here assumes that I've got S different phenotypes in the population that I start with. There's no mutation here. There's no mutation, there's no migration process here at all. So essentially, this is dealing with something called standing genetic variation, in this case, standing phenotypic variation. So you're kind of assuming that what you start with, you can eliminate things from the population, but you're not able to generate any new variation. No mutations can lead to anything new. There's nothing like recombination here that can give you some variation you didn't have before. Okay, so how can we relate this back to evolutionary game theory then? We've got an equation for some dynamics. We want to also think about this process of mutation as well. And this is where adaptive dynamics comes in, okay? So one way to approach this problem is to assume that initially there's a very large population consists of only two phenotypes. And really, actually, we're going to assume that initially there's just one phenotype in the population, which is we're going to call our resident, or the subscript R. So this is very, very common initially, and so has a frequency close to 1. In fact, to start with, it technically has a frequency of 1 because everyone is composed of this particular phenotype. Then we're going to assume that there's a rare mutation, and this mutant, denoted by subscript M, has a frequency close to 0 because it's very rare, and we're going to see if that mutant can invade into this population. This is a little bit like competition in our evolutionary game theory setup where we had two strategies. Here we've got these two phenotypes, our resident and our mutant, and we're going to be thinking about kind of the extremes of what happens when one of these strategies, the mutant, is very, very rare. Can it invade? It's a little bit like when we were looking at our evolutionary stable strategies as well. Okay, so this is where this kind of link comes in. We're going to make some assumptions, though, about this. We're going to assume, for one thing, that our different phenotypes are perfectly heritable. So there are no additional mutations. We think of this mutation as just kind of like a one-off event. No additional mutations. And also that all of the phenotypes breed true. So individuals with the same, with the resident phenotype only produce offspring with the resident phenotype, and similarly for the mutant. You sometimes see this referred to as that they breed true. Okay, so we're just going to think about these two phenotypes for now. What we're going to do then is we're going to compete these two phenotypes to see if they tend to a stable coexistence equilibrium. So it's possible that, we've got this resident in, the mutant comes in, and then they're both able to coexist with each other. The only other two options are, well, they could coexist each other in a stable sense. We're going to assume that one possibility is they coexist. What does that coexistence look like? We will ignore for now. The other two possibilities are that the resident drives the mutant extinct, so the mutant can't invade, or the mutant drives the resident extinct, at which point it will become the new resident. Okay, so there's only these three possibilities. They can coexist somehow, or one will drive the other extinct. And for simplicity, for now, we're just going to assume that coexistence isn't possible. Okay, so either the mutant is going to win or the resident is going to win, and it will drive the other phenotype extinct. Okay, so since the mutant is initially very rare, we can think about its per capita growth rate when it's rare. And this is essentially telling us its fitness. So for it to invade, we need to have its per capita growth rate 1 over PM dPm dt being positive. If it's negative, then it's just going to decay to 0. Remember, this is going to tell us essentially exponential growth or decay. So what's this going to look like? Well, it's going to be the per capita growth rate. Unfortunately, we've got an M for our Malthusian growth rate and an M for our mutants. There's no great notation to do this, but that's why there are two M's here. M sub M, with the little the sub M referring to the fact that this is the mutants per capita growth rate. We have the mutants per capita growth rate for its individuals. Remember, these are all in frequency dynamics. This M sub M is all about number of individuals. Okay. So we need M sub M minus M bar. There is a little there's a kind of like a practicality thing here and a slight mathematical difference here. Up here, I said it drives the mutant extinct. Technically, this is not true down here. In most realistic cases, when we actually do adaptive dynamics, that is actually what is happening. The mutant is being driven extinct. Here, because we've got potentially exponential growth, it could actually be growing exponentially. It's just growing exponentially much slower in the case that it's driven extinct than the dominant type, the resident. In that case, both are growing exponentially. Because one is growing exponentially much faster than the other, its frequency would tend towards 1, and the other one, its frequency would tend towards 0. It's not actually extinct, but that's in a sort of a mathematical sense of things are growing exponentially. We know in real biological populations that exponential growth cannot be maintained indefinitely. Okay, so there's a slight disconnect here between where I said things are extinct versus down here. But functionally, when it comes to actually model these things, we'll have limited resources and things like that, which is more realistic, and therefore one of them will be driven extinct. Okay, so just bear that in mind for now. When I'm saying here that they're driven extinct, really what I'm saying is actually their frequency tends towards 0. Usually extinction and frequency tending towards 0 are the same thing. If they're both growing exponentially, it's not. Okay, that's a little aside. But ultimately here, this M bar, if you recall up here, we assumed that, we assume it, that the resident phenotype has frequency close to 1. So the average growth rate of the population, M bar, is just going to be M sub R, the per capita growth rate of the resident phenotype. This is nice and simple, right? What's your intuition here? When can the mutant invade? Well, if the mutant has a higher per capita growth rate, it will invade. If M sub M is greater than M sub R, this is positive, therefore it can invade. If it has a lower per capita growth rate, then it can't invade. It will decay. in terms of its frequency, will tend towards 0. So this is just one resident population with a mutation, a single mutation, right? And then we've had this mutation, then we see, okay, does that resident population win? Does its frequency tend towards 1? Or does it lose and its frequency tends towards 0, at which point the mutant replaces it effectively, okay, and becomes the dominant type. Its frequency tends towards 1. Recall, we're assuming here that they can't coexist. In fact, in this setup, they can't coexist unless they had identical growth rates, in which case you wouldn't actually be able to get invasion because this would be 0. Okay, so we've determined if a mutant can invade. I say if it becomes the new resident phenotype, what we're going to do is we're going to relabel it as this resident. So the MM that we had before, if it can invade, is now going to become our new MR. What we're going to essentially do is just iterate this process. So we've had this one case of, okay, there was a resident, there's a mutation, we see whether that mutation can invade. We now essentially let time run to infinity. We're going to let everything settle down again. That type will either, that mutant will either go to fixation, a frequency of 1, or it will be driven extinct. If it goes to fixation, it becomes our new resident type. Once everything is settled down, it's either reached fixation or extinction. Then we allow another mutation to occur. And then we just repeat this process. So what we're doing here is something known as a separation of timescales. So we're separating out our ecological and evolutionary dynamics. So really, when we've got these two types competing, this MM and this MR, I think of this as just, because there's a new mutational process going on within this, this is really just ecological dynamics. We've got two sets of individuals, they're competing, one of those will win, one of those will lose. So it's referred to really as ecological dynamics. And then the evolutionary timescale is really the collection of all of these rounds of competition between our residents and mutants over many, many, many steps. So what we're effectively assuming is that mutations are sufficiently rare that the population reaches a steady state before another mutation occurs. If you have lots and lots of mutations occurring, then we'd expect there to be lots and lots of different phenotypes competing at the same time. If mutations are sufficiently rare, that by the time one mutation arises, everything else has kind of settled down. The previous mutant has either won or lost. Okay, so that basically means we only have to think about these two types, which is a nice way of thinking about it rather than having to think of, say, n different types. So this allows us to ignore those dynamics of mutation, only means we have to consider these two different phenotypes. And the second key assumption that we have that's related to mutations is about the size of mutations. And we're going to assume that these mutations are not only rare, but they have small phenotypic effects. So remember, we're modeling phenotypes here rather than genotypes. I'm going to assume that our mutant is essentially very similar to our resident. So if you imagine these as being continuous traits along the real line, we're assuming that there's no big jumps in that your mutant is very, very close to your resident. And not infinitesimally close, but we're assuming that it's pretty damn close. It's not a really big jump line. What this means then is we've got this process that we're iterating over where we start with a mutation. And then if it is able to invade, then it invades. We have invasion, or at least it's tried to invade. And then if it is successful, then it replaces the resident. And then we go back to the start. We have a new mutation. And because we're assuming that our mutant is very similar to our resident population, very small phenotypic effect, if our mutant replaces the resident and then a new mutant arises, what we're essentially doing, again, if you think of that as being like the real line, you're just kind of slowly shifting along that real line. You're not making big jumps, you're just kind of shifting along very slowly. So this means that evolution proceeds in a gradual manner rather than having sudden large changes in phenotype. Sometimes you'll see this referred to in the literature or in textbooks as being a local mutation rather than a global mutation. In other words, it's just a small effect. One of the ways you can justify this as well is that these continuous traits, take something like body size, height, they aren't just determined by one or two genes. So remember when if you go all the way back to our population genetics era, when we were looking at things like eye color or sickle cell trait, Tay-Sachs disease, these things that are determined by, say, just one mutation that might cause a really big change in your phenotype. You know, one allele changes and it changes your eye color. Right? There's a very big change. What we're assuming here really is that there are lots and lots and lots of loci, and they'll have relatively small effects. And those loci all combine together to give you your phenotype of interest. So something like your body size is not just determined by one or two genetic loci, they're determined by many, many, many genetic loci, as well as environmental effects as well. So that means that, you know, if you have a mutation, it's really only just shifting that by a small effect. You can think of this as being, say, a string, a binary string, say, of length n, and each mutation just has an overall effect on your phenotype of like 1 over n, where n is just like the total number of loci, assuming that you can sort of have if you had ones at all of those loci, that would correspond to a phenotype of 1. If you had zeros at all of those loci, it would correspond to a phenotype of 0, and you're kind of like shifting slowly along that. Okay, so these mutations have relatively small effects. So in other words, if our resident has phenotype given by some trait value XR, which I'm going to say is positive here, but that really matters, then XM is just going to equal XR plus or minus epsilon for some small epsilon. Okay. This is the basic setup of adaptive dynamics, and we'll go into this more next lecture and over the coming weeks. Now let's suppose, as an example, that we've got the per capita growth rate of phenotype X is given by some function. I'm not going to say where this function comes from, but suppose it's given by the per capita growth rate of this phenotype is X minus X squared. Suppose this is something like body size. Okay, body size of an insect, or maybe X is measured in centimeters or something like that. And its per capita growth rate is going to depend on that. So perhaps if its body size is too small, it's not going to grow very fast. It's not going to be able to say compete for resources. Maybe if its body size is very large, you know, intuitively you can kind of see maybe what's going to happen. If its body size is very large, then it's not going to be efficient maybe in its use of resources. We say, okay, the per capita growth of that phenotype, an individual phenotype X, is going to be X minus X squared. Question is then, what will happen to the organism's phenotype in the long term? Well, we can kind of walk through this in a verbal way. And essentially what we'll be doing when we do adaptive dynamics is sort of rigorizing this in making this a more mathematical approach rather than just kind of a verbal argument, okay? So kind of recipe we have is, suppose our resident phenotype, XR, is initially small and positive. You were told in the question that it needs to be positive. We know from, we just go back to this replicator equation up here, that any mutant is only going to be able to invade if its per capita growth rate is greater than that of the resident. So a mutant can only invade if M of XM, this is the phenotype XM, is greater than M of XR. So if the per capita growth rate of our mutant is greater than the per capita growth rate of the resident. So in the long term, what might we expect? Well, we'd expect X to converge to the maximum of mx, m of x. So this occurs at x equals x star. Thinking about what this looks like. We have our phenotypes X on the horizontal axis and our per capita growth rate of those phenotypes. We've got a parabola that looks something like this. We know, in fact, that when X is 0 or X is 1, then M of X is going to equal 0. We know we kind of jumped ahead in this kind of analysis here because we know what a quadratic looks like. This is why this is not a particularly rigorous way of doing this. This is kind of that verbal argument. When we get into the details of adaptive dynamics a bit more, we'll talk about things like, does it converge? Essentially, we're kind of assuming that it converges here because we know what a quadratic looks like. We'll get back to this in a bit more detail in future lectures. Here, we can take the derivative of our per capita growth rate function, which we end up with 1 minus 2x. And this is equal to 0 if x star here is equal to a half. This is a half here. You can work out, in fact, what's its growth rate. At this point here, it's per capita growth rate. The maximum is a quarter. So in this case, we would expect x to tend towards x star equals to a half in the long term. One way of thinking about this, if we just zoom in on this little diagram here, is maybe this is my initial value of xr, this purple cross. And then I'm going to say, okay, what happens if there's a rare mutation? So this is my initial xr. And then suppose there's a mutation that occurs just a little bit away from it, say here. Well, this guy here has a higher growth rate, so it can invade. And you can keep repeating this process, right? You can keep introducing mutations, and they're going to step you along. This is this iterative process until eventually you get up to here. Once you get there, a mutation either decreasing or increasing x is always going to lead you to a lower growth rate. So you're kind of like climbing this hill. You can think of this as taking a path up this hill. You get to this top point here. Once you reach that point, any mutation is always just going to lower your growth rate. So once you get there, you stay there. And this is essentially analogous to our ESS that we had before, an evolutionarily stable strategy, right? That we had from our evolutionary game theory. Nothing can invade this. Do you remember one of the conditions that we had going from a Nash equilibrium, a weak Nash equilibrium, to an evolutionarily stable strategy was that it couldn't be invaded, right? We had that additional condition. And that's essentially what's going on here. I talked before, and I will talk again about the idea of fitness peaks and troughs. This is a fitness maximum. Peak. I mentioned that this analysis is a bit oversimplified. We kind of just did a verbal argument and kind of fudge some of the steps a little bit here because we kind of know what a quadratic looks like. In general, you're not going to be able to write down something quite so simple as this. This will come ultimately from some underlying biological processes like births and deaths. We'll have a model that represents these processes. And although functionally what we're doing is we're trying to think about the maximum of fitness, this thing here is actually constant with regards to the environment. So it only depends on the phenotypes that are currently there. It doesn't change over time. That'll be one of the key things. And we've not talked about, this idea of convergence. So it turns out ultimately that whether something converges and whether something is a fitness maximum are actually two separable things. So we have to consider ultimately two types of stability. We'll get onto that after the midterm. But now we're just going to focus on this idea of evolutionary stability, which we'll talk about more on Wednesday. Okay, that's it for today. The key things really to remember today is this switch from evolutionary game theory where we're just thinking about those steady states to this idea of a dynamical process. So this stepping stone kind of model here that I had of mutation, invasion, replacement is kind of what we're going towards with adaptive dynamics. That allows us to not just think about this end state here, if you like, this is kind of what our evolutionary game theory was focused on, but how we actually get there. Like I said, it turns out that just because something is an evolutionarily stable state doesn't mean you can ever actually achieve it. Okay, those two things are not identical. Turns out as well, you can move also towards things that aren't an evolutionarily stable state. We'll get onto this in the future weeks, and this leads to something called branching and diversification. So this can tell us something about why we see coexistence between different types of things in the population or between different species. Okay, that's basically it for today. And yeah, I will see you guys on Wednesday.